No, spontaneous applause is okay, it's acceptable. Well, William Friber's tried to blackmail diploma students to come tonight, but it obviously didn't work, which is quite interesting. I find that quite interesting, because he said, you must come to the lecture because Pete Silver's going to be marking your coursework. And then none of them fell for it, because I can't see any diploma students in the room. Yeah, apart from, yeah, you're all passed? Good? High pass, actually. Yeah, we've got, it's the old Obama. We got all you, but thank you for coming, appreciate it. Yeah, building information model. That's the first model of information I ever came across, and it was when I was a student at the Architectural Association in the 1980s, and computing was, in architecture, was pretty much at its infancy. And we were interested in computers and how they were going to manipulate information for us. And under the tutelage of John Fraser, Professor Fraser, we as a bunch of students built this model of information, which he called, it was his design, it was called the Universal Constructor. And the idea was that we wanted to make a three-dimensional computer screen, if you like, which I still think has never been really done, a true three-dimensional computer screen where you could pixelate in 3 dimensions. It was fairly crude in that respect, but you can see it was made of a series of stackable cubes, each of which had an integrated circuit and some LEDs which could tell you things or display information. When we were designing it, we were looking for the perfect cube, little housing thing. We were going on, well, we weren't going online because I don't think we could, but anyway, we were searching. However we used to search, I can't remember. How did we find information? Books. We looked in books and magazines, and we were in Northern Ireland at the time because John Fraser was teaching at Queen's University. And somebody had gone into a bank to change some money, and they were giving away, the bank were giving away what they called money boxes, Ulster Bank money boxes. They were these little perfect cubes. And the guy said, where are you sourcing them? And they said, oh, it's a factory up. Anyway, we got about 1,000 of these things. I've got a remote control technology. And we built a computer which consisted of a baseboard, which is a 12 by 12 grid, and you could stack each of these little integrated circuits on top of each other to make what was effectively a 3-dimensional model. And I'd quite like to show a little film of it. The thing about the model was that we were trying to display, on the one hand, we wanted to see how information moves through a computer so that it wasn't, so we can demystify the logic paths. And on the other hand, we wanted to be able to use it to animate. And I still think that until now, kill the sound. Sorry. Until to this day, there still isn't such a thing as a truly 3-dimensional screen. You might get stereophonic, and you might get ways of visualizing information virtually in 3 dimensions, but this was a truly 3-dimensional computer. So it's a 12 by 12 grid. In theory, it was 12, each could be stackable to 12 cubes, so that's 12 times 12 times 12, a data space consisting of 12 by 12 by 12. And so what the LEDs were doing was you could address, if you like, any cube in the matrix, in the 12 by 12 by 12 matrix. You could send information to that cube, and the LED would display that it understood where it was in space, which was one very useful thing. And then there were green LEDs and red LEDs, so you could also send a set of instructions into the matrix. You could say, okay, add another cube here, take 2 away here. So it was also a reconfigurable 3-dimensional space. So what you're looking at the moment is you're looking at information actually physically traveling through a 3-dimensional system. You're visualizing what the computer is doing invisibly, if you like. That will do. Yes, come back to one. So this was at a time when computing and architecture was at its infancy. It was the late 1980s. Although computing was fairly advanced, computing wasn't used much in architecture at that time. And so for us, it was quite an interesting time to be involved in architecture. We had drawing boards and people had computers. And these are my first computer drawings, you'd be privileged to know. Some people say it's never got any better, but you know, I don't know. That was fairly purist. It was pre-mice. You didn't have a mouse interface. You had to write. You had to type in a coordinate, you know, as a vector. You had to type in that coordinate, press a button, and boom, the line appeared. And we thought that was fantastic. Line appears. I was very proud of those drawings. And the screen dumps, you could either do, well, you can see orange on black or black and orange. That was it. That was the only possible outputs. But although it was the beginnings of graphic computing, and we didn't have the mouse to interface, it was the beginnings of graphic computing, but what John Fraser was talking to us about was how you use the computer to design. And that was his question. I'm not sure if it was his originally. Just what was it about design, you know, computer-aided design? Just what was it about design that needed aiding in the first place? And one thing we understood very clearly was CAD didn't stand for computer-aided design. It stood originally for computer-aided drafting. The machine was completely and utterly a tool that we would use to, instead of a drawing board and a rotoring pen, it was a tool to produce completed architecture, if you like. It was nothing to do with how my brain thinks as a designer, how I might design something. It was a very useful drafting tool. That's what CAD stood for. And at the same time, we were also fortunate enough to encounter this character, Gordon Pask, Professor Pask, who was associated with the AA, and he was an influence on the making of this universal constructor because he was a cyberneticist. He talked to us about cybernetics, which was I didn't know what it was. Any Greeks in the audience? Cybernetica?
Cybernetics, yeah.
It's a Greek word, isn't it? Yeah. I think it means to navigate in Greek, to find your way through something. And the idea of cybernetics was that their view of the world, and that was the kind of seminal book by Norbert Wiener, called Cybernetics and Society, the human use of human beings. That was their logo, if you like, their dogma. They saw the whole world as information. And it didn't matter whether you were an architect, an economist, an engineer, entrepreneur, it didn't matter. When we look at the world, we're looking at how information moves in people and how machines can be incorporated into that, because machines were just becoming interesting at that time, or machine logic. John Fraser used the terms machine logic and machine intelligence, which I thought was a very exotic way of describing computing. Machine logic and machine intelligence. But Gordon Pask used to say, we have to be very careful here, because machines are doing is they're crunching data. And data is not information, and information is not knowledge. There's a transition, if you like, that's necessary to turn one into the other. We hope you guys are going to end up with this as a result of the data that we give you. And I think what we do is try and turn that, at least that far. Whether you get any knowledge out of it, it remains to be seen. But it relies initially in... The computer would say, if you could interrogate it and ask it what its relationship with you is, it would say to you, as a human, your world is analog and my world is digital. So how do you transform that information, if you like? And these are simple icons of analog and digital. You know, clockwork. Clocks were initially run on clockwork, so you're using the embodied energy in a spring, you're winding up a spring and then controlling it to give you a constant output. But it was still a wave because it's a wound up coil of spring steel that's gradually letting its information out. So that's a wave. That's pure digital. Everything that we see in the world, or that we, no, everything that we don't see in the world, but all the information is traveling in wavelengths, all the information. This is a slightly exaggerated graph of all the information that's out there in terms of waves and wavelengths. And this is the bit that we deal with mainly in architecture. It's a very tiny, tiny fraction of it. Nevertheless, all the information that we have to deal with comes as analog waves. And there's an analogy which may or may not be fair, and Francois keeps saying, find the film of this, but I can't, of the light bulb swinging in a room. Because the light bulb swinging in a room is a point source of, it's one point, it's a pixel, but we never see it as a pixel. We will see the light wave. We will see it constantly moving. And that's, when you look at the tiniest things that we can so far look at, that's exactly what they are. They're both a wave and a particle simultaneously. So that's interesting, I think. And the earliest protagonists of trying to digitize analog information, if you like, were people like Edward Muybridge, who did these studies who managed to use photography to break down wave-type information into bytes, into stages. So this was his study of the horse. And it's not trivial because only when this was done did we begin to understand the horse's gait, the way it moves in space. And it is an extraordinarily complex movement, and it's very different to what we might have imagined in the first place. So these studies not only were very beautiful, digitized analog information, but also helped us learn about how things move in the world. And modern robotics uses this kind of information to make robots that can traverse complicated terrain. My take on it as a student was this technology, which was used at the time for drafting curves, particularly, as you can see, this is sections through a yacht hull. And naval architects would always use these splining rods and weights, which they ironically made look like little lead whales. So to make the spline curve, in order to draw the yacht sections, they used flexible timbers, more latterly nylon rods, and they would weigh them down at particular points. I need that film. And there was something rather elegant about drawing the yacht, drawing the hull of a boat with a material which was timber from which the boat was going to be built. So those spline curves, those curving that rod and drawing it on a drawing board to make the yacht sections, was the material from which the boat would eventually be made. So the direct connection between how you drew it and how you, I didn't particularly want the sound, but never mind. This was a promo video for my diploma project. I don't know why I put sound on, but so this was trying to connect analog and digital. So all of these this linear motion is made by these stepper motors which are moving rods up and down. The stepper motors, strictly called stepping linear actuators, have a worm screw. You can see that threaded rod. Inside there's a motor that's driving the nut, effectively, accurate to 0.05 of a millimeter. This stepper motor, so you can program it to move the rod up and down. So that's a digital driver, and the output is a wave. For the sake of this particular demonstration, it was animated. There was no reason particularly why they should be moving simultaneously. It was just, the intention was just to achieve a particular shape. Nevertheless, that was my take on analog and digital. So in the real world, when we're converting A to D, it's as you can see on the tin here. The analog wave, whatever it is simply broken down into bytes of information, and those bytes of information are coded in binary, which again, of course, is critical to computing. The ones and zeros are absolutely critical. We couldn't do it with old math. We can't do it with the old mathematical alphabet. That doesn't work for us. That does work for us. We tend to use ones and zeros. I've also seen it written that way. Yes and no, truth and lie, doesn't matter. It's just on and off in the end. It's just two states that anything can be in, on or off in the end. So that's how I can digitize an analog wave. Excuse me. Once I can do that, once I can digitize an analog wave, I can start sending instructions into a system. So that's what's residing inside every silicon chip in one way or another of complexity. They're called logic gates. So you're sending information in one end, it's transforming it in one way or another and outputting it in another way. Every integrated circuit has that as its basis, logic gates. So that enables all of your interfacing with your computer. That's what when the computer asks you, how do you transfer analog into digital? All of these are basically what we call A to D converters. They're taking world information in some form or another, video, audio, whatever it is, and making the computer understand it. So back to the thesis. By the way, this lecture, I'm only giving this lecture for the RIBA, and they've all gone home. Not quite. Oh, all right. Good. This is what we're meant to be talking about. Do you believe that? All parties are guaranteed to sing from the same songbook. The reason there's a car here, it's a Lotus Elise? Yeah. It's the best analogy I have. There was a documentary on Lotus when the bosses decided to create this car. The company had been in a lull for a while, and the board said, we need a brand new two-seater sports car. You can start from the ground, you can start from nothing. Empty book. And what they did was what all manufacturers do, you go to the design department and say, design me a car. And by the way, it was meant to have no doors. It was meant to be like a Formula One car that you just jump into. That was kind of part of the spec. Very far. So the design department went off and drew the car, and they brought the drawings back to the board, not the borings back to the drawer. And the board said, fabulous, looks fantastic. Looks like it's going 200 miles an hour when it's stationary. Great. Give it to the guys in the aerodynamics department and see what they make of it. So they take it down. They take the drawings downstairs to the guys in the white coats, and the guys in the white coats make a third scale clay model of the car. Quite a big object, 2 or 3 meters. And they put the clay model in the wind tunnel, and they blow smoke over it. And they watch the smoke traveling over the car, and they look at it for a while, and they went, beautiful, beautiful design. It's got the aerodynamics of a brick. So what they do is in real time, they start, because the clay is still wet, they start sculpting it in the wind tunnel. They take bits off, they add bits on, they gradually change it until they get rid of the turbulence, which is what they don't want. You don't want the smoke to start vortexing around the aerodynamic shape, until they got rid of all the vortices and they've got this perfect aerodynamic car. They take that model back to the designers. The designers look at it and go, oh, it works aerodynamically, but it's ugly as shit. This is not how you want to think in architecture or anything else. It's this really bad way of designing. So there's a toing and froing. Of course, there's compromises, and eventually they did get to a compromise. They designed something, then they took it to the EU Health and Safety guys to check that everything was fine. And of course, the EU health and safety guys said, well, if you want a car without doors, the sill height has to be 4 centimeters higher than what you've designed. Now, to a car designer, 4 centimeters is an awful lot, and it caused immense problems. So between legislation, fabrication, design, computer analysis, this is not a good way to design. Just thought I'd tell you that as architects. The reality with building information modeling is that it's becoming part of our world, because the government, anything that we procure or that we work on through the government will very soon have to have the building information model embedded in it. I'm not sure that the government know how to assess whether the building information model is embedded in the structure or not. It's going to be quite an interesting thing to police. Nevertheless, you can see here it's all about computers again. That's a computer. That used to be the architect. The architect was the person that was meant to speak all those languages. But it's been taken away. So what is he? I don't know. That's going to be interesting. The way we teach it here, or have taught it, is as a series of components. From site investigation through to this area, which we actually don't deal very much in architecture, or they deal with much more downstairs in construction management. But actually everything that you do as architects now can be quantified or qualified as a component of building information modeling. Everything that you do. You may no longer be a part of that equation eventually. I can't see no reason why the computer can't do all that as well. So you might as well go home. Good night. No, one more thing. So here's some examples. This all has to go into the central model from the very beginning. We have to understand the topology of our site. We have to be able to measure it, whether it's artificial or natural. It has to be very accurately measured, and now it can be in 3 dimensions, very accurately measured. We can look at what's there already in terms of its efficiency, thermally and otherwise. We can look at it in terms of, in this case, sound and noise. I haven't got an example, but we can look at it in respect of where the prevailing winds are and so on and so forth. We can do wind mapping. You can go online. You can get examples of that. Will reminded me that we had a lecture last week where they were talking about wind mapping, and of course in the UK there's a prevailing, we call a prevailing wind. The wind tends to come from a particular direction, but every so often we'll get a vicious thing coming from Siberia or somewhere. We have to deal with all those conditions as architects. So that all goes into the model. Different ways of analysing structure go into the model, and that can go right back to material selection, right back to the very beginning, and how you negotiate your way around that. We're also interested in where materials come from, how they're transported to site, so on and so forth. But with these programs, and these programs again were developed for the car and yacht industry particularly, where they look very, very much for efficiency in materials, you work backwards. So instead of saying, okay, I'm going to use a particular material to solve a particular problem, they will say, what's the problem? What are the parameters of it? Can we invent a material to solve the problem? Or can we combine materials in a particular way? So as a student, you would write, using that, you would write a search engine. You'd pass your technical study. You would devise a search engine to solve a particular problem. I want a cantilever, 30 meters, I've got to carry 3 floors. How do I combine those things? So that's one aspect. Most of you are now familiar with form-finding software. That particular one is, I think, an add-on to Vectorworks, where you're looking at tensile membrane structures, and they will give you, the efficiency and so on of the structure. And this is an example of finite element analysis, which is great, again, for us architects who don't like to do number crunching that structural engineers do, but we can visualize, in this case, it was a Perspex tower. Perspex tower, we can get an immediate visualization of the stresses that are the applied stresses on that tower and make adjustments to our construction according to that. So that's very useful for us as architects. Most of you know about environmental analysis by now. We tend to use ecotech in this school as an analytical tool. So we know there's no excuse for not knowing where the sun is, because you can put your three-dimensional model into ecotech. You can put yourself anywhere in the world, anytime, any place. It will give you an immediate analysis of the sun path around your building. And similarly, I think this one is for daylight penetration. So you make an opening in your structure, and you can analyze the amount of daylighting that you can achieve. What else have I got there? Acoustic properties. Yeah. On a slightly more complex level, we can also look at things that are moving. So computational fluid dynamics is what we apply, and this is, for example, this is looking at wind impact on a facade. So, which is critical for our structural analysis in a way. That's very useful. That's an acoustic one, and I think I've got a film of it, Will. So computational fluid dynamics, anything to do with movement. It can be air, it can be sound, it can be people. We had a lecture on Monday on stadium design, where they were talking about the need to get people in and out of a stadium quickly. And very interestingly, the difference between a stadium such as the one designed for the Olympics, where people are there kind of all day, and football stadia, where people suddenly at half-time have to go to the toilet. You're not listening to me, are you? I can see. You're watching this fabulous acoustic. It is the best of the year. I'll do it again. In theory, they were analysing the form and surfaces of the mayor's building. Arabs are doing. So that's a point source of sound. That's a click, and looking at how sound moves. So acoustics are controlled by geometry and surface both together, or an intermix of the two. They have to be careful about things like what happened at the top of 30 St Mary Axe of the Gherkin, as you know it, which is they put a big polycarbonate dome on top, and it's the restaurant. And the bankers all sit in the restaurant having conversations. And what they've realized is that you can have a quiet conversation at a table here, and on the other side, 20 meters away, the guys are hearing everything you say, because it's going like that, which we always knew because of the Whispering Gallery in St Paul's Cathedral. We always knew that in any circular space, sound is going to carry round. So they had to put lots of sound baffles in to prevent secrets being transferred. Will and I are particularly passionately not interested in architecture generating energy. I don't know if I should say that or not, but it's not interesting. If you want to generate energy, build a power station on the moon and beam it to Earth. I mean, that's not interesting. But occasionally, something interesting does come along. Using that analytical software here, this building was designed on plan as a kind of aerofoil. So given that they did want to power it by wind generators, what's the most efficient way of doing it? Well, by designing that particular horizontal section through the building, I can exaggerate the movement of air around the building. So if I pin my, in this case, helical generators on the tail edge, I'm going to get more air working around them. So I think if you are going to do it, that's a kind of nice bit of analysis. You guys are sitting down drawing plans, but actually this plan sort of drew itself. You know, obviously it was a constricted corner site, so it roughly had that kind of shape. They worked with that shape and they thought, okay, we can generate energy literally by the horizontal section through the building. This stuff goes into the building information model, what's known as optimization and clash detection. This is an optimized roof. This was the roof you're probably familiar with over the British Museum, thank you. I think it's Norman Foster. The problem they had was that the circular library in the center of the rectangle wasn't in the center of the rectangle, was slightly wrong. And it's the first time that I've ever seen a parametric modeling as a computer program, because they worked on, Arabs, I think again, devised a program, and I saw it working in real time, where you've got a rectangle, you've got a circle in the middle, you've got this system, which is combination of tangential and other angles to make the triangles, and you pulled on the program, you pulled that circle very slightly off center, and everything started to reconfigure itself around. Now the optimization was, the idea was to, you know, to minimize the variations of triangles. So you're saying to the computer, I want the least number, you know, least possible combinations of triangles to make up this, because the fabrication, to make the fabrication process more efficient. So you give the computer a set of parameters, you work out the algorithm, you pull that circle slightly off center, and you end up with an efficient parametric design. The other part of 3D graphic modeling, as far as BIM is concerned, is what's called clash detection. So if everybody's feeding into this model, the service engineers, M&E, electricians, environmental engineers, structural engineers, are all feeding their information back into the same central model. The model goes, hold on a minute, you've got a column here, I want the water, and it's doing all the adjusting for you, as long as everybody feeds the information into that model. Not only that, every component in the model, when you click on the component, not only is it's an object, graphically it's an object, but it's also an object in that you know who the supplier is, you know where it's coming from, you know how long it's going to take to get to site, and you know what the cost is. So the building specification is all basically tied up in that model. I find clash detection a really strange concept, because I thought that's what we do as architects. I thought that's all we do, is we detect clashes, don't we? And then we design them out. I mean, this room is a very good example. Those windows open, those don't. Why don't they? What? Well, pollution and noise. Yeah, noise pollution and real pollution. If we open those, I theoretically can't give a lecture because but if I could open them both, I get cross ventilation, I get natural ventilation, which would be ideal. You solve it, as an architect, solve that problem. Solve it elegantly and interestingly, rather than sealing those off and putting in thousands and thousands of pounds worth of air conditioning into this room. I could do without all of that if I could open those windows and prevent noise coming in. And I've said this many times to you guys, we deal with, architecture deals with conflicting criteria, and the way we solve conflicting criteria is some of the most creative things we do. So I'm not sure whether we should let computers do that. I'm not sure. This goes into the model as well. We mainly deal with this stuff. We're interested in this, off-site prefabrication, CIM. You've got machines here that can simulate it, which is great. The guys downstairs deal more with this stuff, although it's interesting, and I think we should probably be more involved with it. Everything goes into the model, and the interesting thing about this stuff is that you run the movie. You actually look at the sequence, the critical path of construction, which I'm constantly trying to encourage diploma students to do, not just to look at, okay, I've built a building, there it is. how do we get to that point? You know, when we're not structural engineers, but we can look at the construction process. So I do think that's important. Here's some examples, some early examples of using digital fabrication. It's one of the earliest I know. It was 1990, I think. This was built for the Seville Expo in Spain by Peter Rice. That filigree arch simply could not have been built without the very, very fine stone cutting that meant that none of these had to be glued together. These are all stacked. And of course, he did that very elegant thing that I've been talking to first-year students about recently, about taking the tension outside what is effectively a low tensile material, stone, taking it all out, expressing it with wire, with steel. That's one of the first examples I know of where digital fabrication has an effect on the architecture. It's not just, oh, I can make this quickly and efficiently and cheaply, but actually I can do something in architecture that I could never have done before. I've got a machine that can do something interesting. That's another example that I've used a number of times. I'm not going to talk about this color change. You guys know. Do you know? Surely you know this story. Say yes if you've heard it more than twice. Yeah, that's enough already. Oh, all right. Well, the Dutch, the Dutch are kind of different to it. Any Dutch in the audience? Shame, really. We like the Dutch. Lars Sproybrook was commissioned to make an emblem for a city, you know, to make a kind of landmark for a village, actually. So he designed this object, and he said, I want it to be interactive. The way I'm going to make it interactive is that the village, it will have color coding according to how the village feels when it wakes up in the morning. So they have they all go, every morning, in theory, everyone in this village wakes up, goes to their computer, goes, I'm feeling a bit miserable this morning. And they type in, it all goes to a central database. The computer goes, 60% of the village are feeling miserable, I'm going green, or whatever it is. And the next morning, oh, no, that's Sunday morning after a heavy night. We're going a bit red. And somehow, so there's a feedback, which is quite interesting, because you kind of go out into your town that day and you go, oh, it's blue, everybody's a bit, maybe we should cheer them up. So it's architecture feeding back, but the real reason for showing it is because, again, it was early-ish, did good digital fabrication, large prefabricated FRP, GRP panels. Lars described it as a Gothic building, which is quite interesting because in structural terms it is actually a vault. It's a kind of vaulting structure. So he kind of he described it as modern Gothic architecture. This is another example that I actually talked about today to the first years. Perforated bridge. That's the Excel spreadsheet for all the tiny holes that were pierced into the bridge to make it light and efficient. Boom, enough of that. And here's the sort of one of the most up-to-date examples of the whole process working together, where it's a prefabricated building. So from the fabricators who are doing the off-site making through the computer program, which knows, again, as I said, every element, knows where it is, where it was made, how long is it going to take to get to site. It's totally all-inclusive BIM model, prefabricated model. And finally, well, this is quite a long outro, trust me. There's a connection with the people that commission buildings or procure buildings in BIM. So while you're doing all this stuff, analyzing, parametric design, and everything else, that's all constantly being fed back to your client, who's able to see it, which is nice for a change. And something that we as architects are really not very good at is considering that when a building's built, it's just beginning its life. We kind of we design these things, thank you very much, good night. That's the beginning. You've romantically, you've given life to something. It's starting. At that moment, it's starting. So facilities management, I don't hear a lot of conversation about facilities management on this floor, anyway. FM. It's known as FM. You go down 2 floors, all they talk about is FM, and none of us know what it is. Once you hand over a building, it's beginning its life, and we've given it all sorts of stuff that has a life. Some bits have longer life than others. And the thing that the government are quite interested in at the moment is this thing about barcoding construction elements, so that if you need to replace something or you know where it's sourced and so on, so it makes it more easier, which is, I think, reasonable. I think it's fair enough. But it's actually more complicated than that, and we architects know that. We know that buildings are becoming more dynamic, more responsive. Actually, we're giving them more of a life than we used to give. We used to give them they were static, almost sculptural objects. You bang them, you put them down. What happens, happens. They might evolve, they might degrade, they might mature, they might not, they might fail. But more and more, we're interested in actually these kinds of things. This is a drawing by Chris Leung that kind of encapsulates that interreaction between the built envelope and the occupiers of that built envelope. It's becoming complex, but because of computing, we are becoming potentially more in control of it. And that's, anyone know what that is? The governor. Everyone come across that object? Yeah, it lifts itself, funnily enough. It's a flyball governor. It's called a flyball governor, and it was the reason it's very important in this context, it was one of the first feedback mechanisms. So if a train was going down a hill, the wheels started traveling faster than the motor, and the engine would brake up. And somebody had a very clever idea. It works on centrifugal force. The faster the thing goes, the faster it rotates. These lift a valve that reduces the amount of energy going into the engine. So it was a really elegant feedback loop that stopped engines braking. So in cybernetics and in any feedback system, it's a sort of icon that we use to describe it. And a lot of you might know this. Cedric Price's Fun Palace. Slightly vague. Do you know, have you been to your cultural context lectures? No, it's not looking good, is it? Should have been. Cedric Price, back in 1960, conceived of truly dynamic buildings that could evolve and change according to use, according to occupancy. So it was a big machine. I mean, really a big machine. Big space frame structure, cranes, things lifting, things could move, things could change. If you presented this to the guys downstairs, to construction management, oh, by the way, it's going to change every day. Things are moving, they would go, this is like one big elevator. No, we're really not interested. It's kind of scary. But Cedric had another very interesting kind of line on this, which was, he said, well, if the building was intelligent, was really intelligent, it could start changing itself. It doesn't need you to, it could start making creative gestures towards you. And in the worst case scenario, it could really bored with what's going on inside and just self-destruct. Just commit suicide. These people are just really not interesting. I'm going to, which I think is interesting. So I've made a matrix just to help you guys understand all the possible ways in which facilities management are going to have to deal with us architects in the future. It's a kind of matrix. Quickly run through it. these systems are quite common now. Computers will already have predetermined programs working in them that will determine what happens over a period of time for that particular piece of built environment. So obviously it's controlling traffic lights. Again, this came up earlier on in a lecture today, where the computer's tracking the sun, always knows where the sun is, sending light down into an atrium, that's the HSBC building. It generally knows what the tides are doing, so it's opening and closing these big gates. The next level up is it's responding to some kind of information. So we call those expert systems. We know where the sun is, we generally know what we want to do with traffic, we generally know what the tides are doing, that just runs on a clock. The next level up is where we're actually responding. So you always need a clock in any kind of logic system. There's got to be that ticking thing, which I found out when I tried to wire in a sensor in my house recently, and there were 3 wires coming out of it and only 2 coming from the lighting circuit. And I went, wait. And I eventually got this Sparky in, said, look. And he said, no, power, you need a clock. Whatever happens here, on, off, yes, I sense you coming, I turn the light on. Whatever happens here, it still needs that constant pulse. You always need a power line, so you always need the clock. I've described that one. Here's some other response systems. Radiator thermostats. That's actually a state change material which changes from dark to light according to light input. That's interesting. That's a yacht mast that is made with minimal amount of structure. It's not designed for the worst gale. It's designed with a minimal structure, but when the wind blows very strongly, inside there are tensile wires that will tense, just like a human body does. Human body's not constantly tense. Otherwise, you're using a lot of energy when you do that. And buildings mostly are doing that all the time. But they can actually relax, and when it gets really windy, they go, which is less energy, less energy to produce that mast. That's a minimal structure. That's self-repairing concrete. So we put into the concrete a material that if there's any cracking and any air, it notices any air, the air will immediately activate the chemical and solidify the chemical, which will fill the crack. And this is kind of the interesting bit where the environment becomes quite intelligent and can start to literally analyze, not just knee-jerk, not just react immediately to what's around it, but begin to learn from what's around it. So this is again the computational fluid dynamics, looking at crowd control, looking at how lots of people move through a space. I couldn't find an artificial example of environmental adaptation except the wonderful camel, who's very, very well adapted for his environment because he's got 2 sets of eyelashes to keep the sand out of his eyes. He carries his water tanks on his back wherever he goes, and so on and so on. And a dynamic Formula One racing car that is sending information back to base all the time, and base is constantly making adjustments in relation to it. Anyway, that was that. So what do you have in your weaponry for dynamic facilities management stuff? You now have state change materials. You can send an electronic impulse into the material and make it, for example, change from liquid to solid, which can control all sorts of, can do shape changing as well as other things. You have all sorts of smart materials that can also do this state change stuff. This is a very old one that probably you encountered at school, which is when you just bond 2 materials together with different coefficients of expansion, and you heat them. You can create a bend. And here is muscle wire, which is where you send a very, very tiny electronic pulse, and you can expand or contract the wire. So these are, if you like, control mechanisms for buildings. Shape memory, alloys and plastics. are alloys and plastics that can remember the first shape that they were manufactured in. So with a car bumper, for example, you can have an accident, you can dent it, you take it back to the factory, they put it in the kiln, heat it up, and it will pop back to the shape that it originally had. It always wants to can go back to its original shape. There's some quite old-fashioned control devices. Wax-actuated ventilation, which has been used since Victorian times in greenhouses. I don't think that's actually a wax. It might be. I think in this tube you have wax. So when it gets hot, too hot, the wax melts, the tube opens up, the window opens, you get air into the greenhouse. Immediate response mechanism. That's been around for a long, long, long time. And this is a building by Jean Prouvé, where all the cladding panels, again, do the same sort of thing as that. Rather than make what we do now, which is expansion joints to allow differential movement for different materials, Prouvé just said, well, these panels can sort of pop. They curve out when they heat. So we don't need to have expansion. So it's a very dynamic facade. It actually changes shape when it gets hot. When it warms up, the whole facade slightly pops out and exaggerates. Solves the problem by a state change material. Slightly theoretically more intelligent ones, that's, you might know, is Jean Nouvel's Arab Institute in Paris, which controls light with irises, which never worked, I don't think, did it? Kind of got stuck at some point. This is a school in South London with an ETFE roof consisting of 3 layers of ETFE, which when it senses too much sunlight, the layers which have a checkerboard pattern, alternate checkerboard patterns, they take air out because these are inflated panels. They take air out, they come closer together, and they darken the space. So they shade the space according to their reading of how much sun is entering the building. So it's a sort of quite intelligent self-shading system. And being a man who likes loud music, I kind of think this is quite interesting because you can create a dynamic acoustic space by mechanically controlling the form of the structure above you. Oh, Will, this is your shout. It's getting less and less like facilities management, more and more like weird stuff, isn't it? Yeah, we're looking at that. So we want to make buildings that are more intelligent, more interactive, more responsive to the people that are in them. This was a project by Josephine Pletz that was made at the Bartlett. It's quite a number of years ago. She called it a virtual pond, but it was basically an interactive gridded floor that you could walk across, and it was as if you were walking across water, if you like. It was as if you were walking across water. What's the material? The floor was just a series of sensors with effectively a white sheet over it, so you couldn't see them. So as you walked, the sensors send information to a computer, the computer sends it up to a projector, the projector sends it to a 45-degree mirror, which beams it back down in real time, instant. So as you go like that, you get the rippling. You know, I think if you want to relax, you don't want a learning lounge, do you? You want to surely. Yeah, back to, enough of that. Oh, yeah, sorry. You want a virtual pond if you want to relax. I would have thought. Ooh. It was a lot of fun. Or, even better, you don't want a learning lounge. You want a wall of chattering teeth to walk past, to excite you. And again, this is a Bartlett project, Tony White. This is one of the very few projects I've ever tutored that actually got into a national newspaper because they thought it was a bit of fun. And
get a politician to stand in front of it.
Yeah, they did actually. It wasn't Boris, it was before Boris Johnson. Boris would love it. We should bring it back. Walls and walls of chattering teeth. Anyway, it's a dynamic facilities management problem. Keep bringing it back to. It's a dynamic they have to maintain this facilities management because you all want a chattering teeth wall to walk past to cheer you up when you arrive in the building in the morning. The clever thing about this is there's only one sensor. There's a sensor, I think the first one hears you, and the next one hears that one, and that hears that. And so as you walk past it, it kind of grew in crescendo. So they'd start like, and it went bonkers as you went past, and then it faded away as you... Much better than a learning lounge, don't you think? And he passed his technical study with these nice circuit diagrams, section, bit of writing. It's not hard to pass your... The RIBA still here? God, I hope not. Not hard to pass your technical study. And then, of course, you may give it a solar collector so it can be autonomous and run around on its own. And the best one of all, unfortunately, I don't know if you came to last week's lecture with the interactive design guys. Doesn't look promising. I was kind of try and show them up, really, but I can't. Because we designed, again, this was last century, I think, an interactive space. We always start with the gridded floor. It's very simple. These are pressure sensors. I've always been surprised that B&Q don't sell ready-made pressure sensor floors, because if you always know where you are in a building. You can always locate somebody. You know how many people they are. You know kind of what they're. That's a great little input device and not very hard to develop. You always know where somebody is and what they're doing. You can turn the lights on. You can do all sorts of stuff. So we start with the gridded floor. So we gridded the floor of actually, it was a coffee bar in Exmouth Market, as it happens. They kindly gave us a space to work in. There's the gridded floor, and we thought, wouldn't it be nice to go into this coffee bar and think you were on a desert island somewhere? And it was on there. So there was water, and there were swaying palm trees. That was the idea. Shall we run the movie? That was a still from it. That's the. Oh, can you fill the screen or not? That's looking into the lagoon, the virtual lagoon, where there are strange. They were fish bowls actually. All right, okay, not quite a lagoon, with strange condom-like jellyfish. To be fair. So what happened? There were a number of these in the space, about 8 or 9, and as you came up to them, as you approached them, they kind of knew you were there because the floor told you there were people coming up towards them, and you can see that there's a tiny little servo motor here. I should credit a guy called Chris Leung who did most of the programming for this. That's the servo motor. So the servo motor, so there was a sensor that knew you were approaching the lagoon, if you like. And as you approach the lagoon, the servo motor got more excited. Here are the palm trees, you see? Okay, come on, use your imagination. There's the lagoon, there's the palm trees. They obviously elastic rods, which are always great for these kinds of things because they're sort of slightly unpredictable. So as you approached here, this end of the table, this one would know that you were getting close, and it all started to get a bit excited. Can you see? But it was more complex than that because at the very top of every rod there was also a proximity sensor that knew what the tree next to it was doing, was getting a bit agitated. So it would also, there was a very complex programming going on between you as an interface and each tree as an interface. And so we were hoping to replicate, if you like, nature as near as we could because it was slightly chaotic. It's not perfectly, nothing was perfectly programmed. There was this element of maybe, going on. Thank you very much. Good night. You can have questions, but